Okay, let's get started on chapters 13, 14, and 15, gears. Now, how are we going to cover three chapters in 1 3 hour period? Well, we're obviously going to skip a lot of material. Um, the material on gears, you could have a whole course in gears. As a matter of fact, that might be an upcoming technical elective in the program, MET program. But this gears is something people still do PhDs in. And one guy in particular, Bob White at John Deere, is in charge of their transmission research laboratory. So the John Deere Transmission Research Laboratory supervisor is a friend of mine, and he reviewed these slides, and so did one of his trainers when they train new transmission engineers. So that supervisor reviewed these slides. I got some good input from him, and he agreed that this is about all you can pack into a 2.5 or 3 hour introductory lecture on gears. And yeah, I incorporated some of their ideas from John Deere in here as well. So I just want to give them a shout out and some credit here for helping me fine tune these slides. Um, so without any further ado, I kind of like this picture. We've got everything from humongous gears in things like radio telescopes, telescopes that are 300 yards wide or bigger, with extremely large building-sized or bigger gear sets, all the way down to nano gears. And if you're interested, here's the source. That is an actual dust mite. He's not actually working on his transmission, but it is an actual photo of a dust mite and nano gears. That's what a dust mite looks like. That's why you ought to wash your sheets once a week, because those things are, otherwise they're living in there and shedding all sorts of stuff in your sheets after they eat your dead skin that will give you all sorts of allergies and respiratory problems. They do exist. There's a picture of one, and believe it or not, they can actually form gears that are smaller than a dust mite by about an order of magnitude, which is pretty darn impressive, if you ask me. I'm not sure what you do with those. Maybe the dust mite knows. Anyhow, here's some types of gears. We've got spur. These are the most typical ones you're probably familiar with. Helical, these look like spur, but the teeth are cut in a helix at an seemingly looking like at an angle, but it's actually in the shape of a helix. We'll get into why later. There's bevel gears and worm gears. Those are the four of the main types there. This is really important to. So this is one of those again final exam type questions. Like what's the name three things that are part of the nomenclature of spur gear teeth or things, something like that. But you really ought to look at this uh, picture in the book and become familiar with the terms. So these are all important terms. And if you have a gear that fails, it's important that you're able to describe where it's failing, probably over the phone or perhaps even with a picture to the OEM, so that they can help you troubleshoot what's actually going wrong with your gear train. Um, but you notice that there's a couple other terms here. One that I added here, I don't think is in the book. That's backlash. So the backlash is this little bit of space right here. So if you have the teeth in contact over where this red dot is on the back side of that, the non-contact side, there has to be a little bit of space. That's called backlash. Um, when you reverse direction, a couple things happen, or if you have high vibration, uh, if you reverse direction, you have an impact because there's some space there that it has to travel through before they touch, going the opposite direction. That can cause some problems. And also, if you have some sort of unsteady operation, you can have the two opposing faces impacting into the opposite gear, and that can cause all sorts of bad stuff: early wear, early fatigue, early gear death. Other than that, we've got our couple of important things here: the dedendum circle, the pitch circle. Um, the pitch circle is basically, you want to think about it. That's the business circle of the gear. So you'll get contact along a good portion of the face, but the line of contact always goes through the pitch circle. So then there's addendum and dedendum, the portions of the tooth above and below the pitch circle. And again, there's circular pitch. That's like a thread pitch. It's the distance between gear teeth taken at the pitch circle, and the tooth thickness is also taken at the pitch circle. So even though there's a variable width tooth, tooth thickness is taken at the pitch circle. I think we had addendum circle down here, and then addendum circle, the top of the tooth, face and flank, which are the portions that are in contact above and below the pitch circle. And we have to have a little bit of clearance and a fillet radius. These are important. If you don't have any clearance, then the mating gear will smash into the root of the gear next to it. So, and then the fillet radius is for stress relief, so that is less likely to become a fatigue failure zone. Only two things I haven't really mentioned yet: face width and top land, pretty and bottom land. Those three are all pretty uh, pretty self-explanatory. Conjugate action. This is a weird picture. It certainly doesn't look like two gear teeth, and it really isn't. It's just showing you that the conjugate action that gear teeth enjoy uh, isn't unique to only gear teeth. There's other other surfaces that, when they roll or slide against each other, they produce a constant angular velocity ratio. If that's what they're doing, then they're said to have conjugate action. And they have a constant angular velocity ratio, which you can define as the radii to point P. P is where the two pitch circles intersect. So you have one pitch circle here and another pitch circle here, and that is point P, just in case it wasn't clear on that. So R1 and R2 that we're talking about. Let me get rid of that P. This is point P. So you have your two pitch circles, radii, and the angular velocity, constant angular velocity ratio is determined by the ratio of the pitch circles. Let's see here. In order to get this conjugate action in gears, we use the involute shape, and that'll be described on the next slide. So the involute profile. This is the most common profile for gear teeth. I've actually formed one of these in SolidWorks, and there's not, so SolidWorks does not have an involute function. So SolidWorks does not have involute function, which is really unfortunate because it is extremely labor intensive to lay these out in SolidWorks. I've done it myself. I actually, for ESC 120, I designed a involute profile for a water turbine that was being used as, part of the ESC 120 Introduction to Design course. So it's actually it's very labor intensive and requires lots of construction lines. So typically, you're not going to want to have to design your own involute. The way it's generated is imagine that you have a string wrapped around a cylinder, and as you keep it taut, you unwind it, and you track the end of the string. So as you can imagine, the string gets longer. The radius with which it's rotating, as the string separates going along this way, its length changes. So the curvature that it produces will change. And this is called an involute. So you have a string wrapped around a cylinder, you hold the string tight and unwrap it from the cylinder and track the end of the string. That'll give you an involute shape or an involute profile. The circle that you're unwrapping it from is called the base circle. So the circle of the cylinder, or the cylinder, that's the base circle. That's what the string is being unwrapped from. Okay, so this is just giving you some background on how these surfaces might meet up. Showing you that you have two involute profiles, touching now. In this case, they have it drawn such that there'd be some horrible interference. But the main part I want to just point out here is the concept of each gear has its own base circle and pitch circle, and the pitch circles have to intersect at point P. And when the teeth are finally cut, you pretty much need to make sure that they don't interfere like this. But that base circle, you might actually be cutting below the base circle in order to give some clearance. So keep that in mind. This is a little bit better representation. Again, there's a lot going on in this graphic. They're showing things that we saw before on the close-up of gear teeth, namely, addendum circles, base circle, pitch circle. You notice, like I said, the dedendum circle is different than the base circle. So the base circle, it's what is forming the tooth, and the dedendum circle is how deep you cut it, and you want to cut it a little deeper, obviously, than the base circle. Otherwise, you'd have horrible interference and teeth cutting the other teeth. So a couple things here. The first point of contact is A. That's over here. That's where the flank of the pinion touches the tip of the gear. And then the last point here is B. That's the last point of contact. And that forms the line of action. AB is the line of action, and that also forms the pressure line. So we can call this the pressure line slash line of action. That's this thing here. And of course, the intersection of the pitch circles needs to be at the intersection of the point P, the pitch circles need to intersect. Now you notice the contact point pretty much moves in a straight line. It moves from A to P to B, and at every point in between, it has a constant line of action. So the contact point is actually traveling in a straight line. That's kind of interesting. Now, keep in mind with this type of, even though the the diameter or the distance of the contact away from the center of the gear and pinion is changing, that the angular velocity ratio is constant. That's extremely interesting. It's more complex than meets the eye here how that happens, but that's essentially the miracle of conjugate action. Um, so let's see here. We have angle of action is the sum of the angle of approach and the angle of recess. So that's these terms here. Again, they go over all the basics for the gear and the pinion. Any portion of the contact that's not conjugate is called interference. This is bad. So if you have undercutting, essentially that means that you're cutting at the root of one of the teeth or all the teeth on one of the pinion or the gear. And undercutting definitely weakens the gear tooth, this last thing. So you don't want interference, that's for sure. Okay. A rack. What's interesting about a rack is that it's basically a spur gear with a pitch diameter of infinity. And what's interesting is you have this involute shape here on the spinning gear. So this is, let me get rid of that, sorry. You have this involute shape or profile, but these are straight. No curve. So when you have a rack, the teeth are going to be straight lines. And they have the pitch of the rack, which they're calling, well, they have a circular pitch and the base pitch. So circular pitch, base pitch, the relation between those is given with equation 1337. So that's the distance between, the base pitch is the distance between the flats, whereas the pitch circle, this is basically a pitch line. So this is a pitch line, and that intersects the pitch circle of the gear. And the distance between the gear teeth along that pitch line is the circular pitch of the rack. Internal gearing, this does have a involute, so this is involute shape or profile, however you want to call it, but otherwise has all the same stuff, addendum, dedendum, it's all kind of reversed here, but you can have an internal gear like this. It has all the same things, and in this case, the base circle is kind of, like I said, everything's flipped. So the base circle's outside of the tip of the gears, the internal gear teeth, but other than that, it's still just an involute shape. Forming versus cutting of gear teeth. So for low wear and a low power transmission and relatively low accuracy of transmitted motion, you have a whole bunch of different methods here, from sand casting to extrusion to powder metallurgy, all sorts of stuff like that. That's basically your mass-produced cheapo gears that don't see a heavy-duty environment or heavy-duty power transmission. However, if you do have higher requirements, then you have to go to things like milling, shaping, hobbing and forging. And I would say it's probably mostly hobbing and forging, um, and for uh, heavier duty gear sets. If it seems like I'm kind of bouncing around here, it's because that's unfortunately what the book does too. It does that over three entire chapters. So I'm loosely following the chapter outline here. They transition to straight bevel gears at this point. And if you're following along in the book, you'll notice that I'm skipping a significant amount of equations, formulations, derivations, explanations, and just you know entire parts of sections are missing. You're only responsible for what's in these slides in this chapter. There's way too much information in chapters 13, 14, and 15 to reasonably pack all three of those chapters in their entirety into a semester course that's not entirely focused on gears. So, we're going to skip around here a little bit, and now we're skipping on to straight bevel gears. And obviously, you'd want to use these to transmit motion between intersecting shafts, meaning shafts that are at 90 degrees from one another. We have parallel helical gears. Again, here's the, notice the helix angle here. This will add an axial force component to the shaft and bearing. So if the trade-off for including, there's a couple trade-offs for including a helix to your gear set. One is that it's more expensive. Helical gears are just more expensive, and it also add an axial force. So you need to have a thrust bearing. But the payoff is that there's a smoother transition between the mating teeth due to the gradual engagement and disengagement. And what that boils down to is what you're paying extra for is less vibration, wear, noise, and a longer life. So you'll find these kind of gears in, for instance, you know, high reliability, low noise applications. Like I would guess helicopter transmissions are probably all helical gears. They're not going to put any spur gears in there, I wouldn't think. Um, they want it quiet and they want it with a long life, obviously, because the thing's flying. So, something like that, you'd pay the extra for the helical gears. Worm gears, um, there's some terminology here, like the lead angle and the helix angle and the pitch. And the pitch diameter. Just one thing I want to point out, that when you see these capital N's, that's number of teeth. So that would be the diameter of the gear. D sub G is diameter of gear. As opposed to the worm. This is the number of teeth in the gear, which is the circular part down here. This is the gear. This is the worm. And they're showing the worm in two views. So this is the side view. And this is the head-on view right there. So that's not two different components. This is the same component. So this is this and this are the same component. The worm just shown in a different view, so you can get the side view. So this is just telling you how to calculate what diameter is required for your worm gear. And some terminology on here that's important, but a whole bunch of equations skipped. They've got some tables, 13.1 through 13.5. These are like standard tooth systems, tooth sizes, proportions, for spur gears, bevel gears, helical gears, and worm gears. My synopsis on these tables is that they're a good double check for any gears you might specify. I think it's highly unlikely that you're going to design your own gear teeth. That's another reason why we're kind of skipping through a lot of the stuff, but um, you're probably going to just spec out a gearbox or contact an OEM and tell them what you need and they'll hook you up. Um, but if in the unlikely event you need to design your own single pair of gears, that's going to require some significant design attention. Um, so the chances of you using these tables is pretty remote. Just spec out a gearbox. It's important that you know what's in the gearbox, and that if the gearbox fails, you have some understanding to diagnose why it's failing. But it's highly unlikely that any of you will be designing a gearbox from scratch. Um, that's highly specialized. Uh, that would be you got a job with a gear manufacturer and they trained you for 10 years. Then maybe somebody would let you design your own gearbox. But other than that, it's usually easier just to, like I said here, spec out a gearbox, know the nomenclature and the topography, geography of gears, uh, and that way, if you have a failure or some unexpected behavior, you have some starting understanding of solving the problem. Um, so you might think in the world of 3D printing, this is generally not a good idea. Typically, 3D printed gears, the people who are putting together the profiles for those teeth are approximating some sort of volute, but it's not involute shape. Like I said, I've done an involute in SolidWorks, and it takes a significant amount of time to lay that out. You need a gazillion, uh, approximately a gazillion construction lines. It's you have to know what you're doing, um, and it's not very easy to change it if you decide to like change your entire base circle diameter. You pretty much have to start all over from step one. So it's each time you want to form an involute shape, you pretty much have to do it all from scratch. It's not fun. It's not easy. It's a whole bunch of work, and you have to know what you're doing. And if you screw it up at step two, and you're already at step 50, you pretty much have to go back to step two. So I would be very wary of 3D printings. I can almost guarantee you that anything that's 3D printed and cheap is not an involute shape. So it's basically not going to be able to transmit anything serious. It'd be like a decoration, like a paperweight. Yeah. So these things are basically just fancy things to put on your desk to show that you're a gearhead, and that's about the limit of their usefulness. If you actually press any of this into actual um, meaningful service, the teeth will just, because they're not involute, they will simply just rip each other to shreds in a matter of seconds if you were to put any kind of normal speed or power through a non-involute shape gear set. This is a useful equation here for gear trains. If we say that the pinion is driving, so the pinion 2 is driving the gear 3, then the speed of 3, so N, capital N, was number of teeth. Little n is rotational speed. Usually in RPM, revolutions per minute. Uh, and D would be the pitch diameters. So here we can get the input and output speed ratio. So this is the N2 is the input speed, and N3 is the output speed. So you can see how this is a pretty useful equation. It's pretty simple for calculating input and output speed. Um, so there's nothing really much more complicated to it beyond that, unless we get a gear train, um, and in which case they just stack up. So you can see that this is just a, uh, a stack up of the different mating pairs, and what it boils down to is essentially this, where N sub L is the last gear in the train, speed. N sub F is the first gear in the train speed. And E is this sucker here. The product of the driving tooth numbers divided by the product of the driven tooth numbers. And one note here is note that gear number 3 is an idler, and that it cancels itself out. That's why it's defined as an idler. All it's doing is reversing the direction. And so when you have that, that's why you need to add that. So in the previous example, the practical limit for one pair of gears is 10 to 1. You can get better than that with almost as many shafts by putting 2 gears on the same shaft, like you have here, a compound gear train. Same thing. E has not changed, so this is the same. This is the same. And with a compound gear set, you can get easily gear ratios up to 100 to 1 in a same size package as the previous slide, which could go up to like 10 to 1. So by compounding the gears onto the same shaft, so this is 2 gears on one shaft, and you could have multiple compound gear sets. I've seen them out in the field myself. It's actually one as a case study at the end of this lecture. And speaking about the end of the lecture, we're almost about halfway through the lecture. So I'm probably going to finish up part 1 here with a compound reverted gear train. This is a more complex design task where you have inline, you have inline shafts. So these are inline. These are really slick. They're compact, and you can get some serious speed reduction in a really compact package. There's just, if you're going to have them in line like that, there's just one additional constraint, and that's that the total number of teeth on the left side has to be equal to the total number of teeth on the right side here. And you can again stack these up, multiple compounding gear sets to get some crazy, insane gear reductions. And I think that's going to do it. Yeah, okay, so we're going into planetary next. So I'm going to back up here, and I'm going to call that the end of chapters 13, 14, and 15, part 1. And then we'll continue. So we're on slide 19 out of, I think, 37. So we're roughly halfway through. So I'm going to cut it here, and we'll pick it up with part 2 after that.